On the morning of September 1st, 1859, Richard Carrington stood in his private observatory in Red Hill, Surrey, doing what he did every clear day, sketching sunspots through his telescope. At 33 years old, Carrington was already one of Britain's most respected amateur astronomers, methodically documenting the sun's activity with the precision of a Victorian gentleman scientist. At 11:18 a.m., something extraordinary happened. Two brilliant white lights erupted from a cluster of sunspots, so intense they were visible against the sun's blazing surface. Carrington had never seen anything like it. He called for his assistant, but by the time the man arrived, the lights were already fading. The entire event lasted less than 5 minutes. Carrington carefully recorded what he had witnessed, sketching the position and intensity of the flare. He had no idea he had just observed the most powerful solar storm in recorded history, an event that would, within hours, bring the world's most advanced technology to its knees and paint the sky with lights visible from the tropics to the poles. What Carrington didn't know was that he had witnessed a coronal mass ejection, a massive burst of plasma and magnetic field released from the sun's corona. This invisible wave of charged particles was hurtling through space toward Earth at over 1,000,000 miles per hour. The collision between this solar tsunami and our planet's magnetic field would create what scientists now call the Carrington Event, named in honor of the man who first observed its cause. But to understand the true magnitude of what was about to unfold, we must first understand the world of 1859. This was the height of the Victorian era, a time of unprecedented technological advancement. The telegraph had revolutionized communication, connecting distant cities and even continents through an intricate web of copper wires. Just 13 years earlier, the first successful transatlantic telegraph cable had been laid, though it had failed after only a few weeks of operation. By 1859, telegraph lines crisscrossed the United States, Europe, and much of the civilized world. These networks carried vital information: news, business transactions, government communications, and personal messages. The telegraph was to the 19th century what the Internet would become to the 21st, the backbone of modern civilization. The particles from Carrington's solar flare reached Earth approximately 18 hours later, at around 5 a.m. on September 2nd. The impact was immediate and spectacular. From the Arctic Circle to the Caribbean, from Europe to Australia, the night sky erupted in brilliant displays of aurora, the northern and southern lights on a scale never before recorded. In New York City, the aurora was so bright that people could read newspapers by its light. Gold miners in the Rocky Mountains woke up thinking it was dawn and began preparing breakfast, only to realize it was still the middle of the night. In Rome, the aurora was so intense that Pope Pius IX was called from his chambers to witness what many believed was a sign from heaven. Caribbean islanders, who had never seen aurora in their tropical skies, watched in wonder and terror as curtains of green and red light danced overhead. But the beautiful light show was merely the visible symptom of something far more sinister happening to the Earth's magnetic field. The charged particles from the sun were interacting violently with our planet's magnetosphere, creating powerful electrical currents in the atmosphere. These currents, in turn, induced massive electrical surges in any long metallic conductor on the ground, particularly telegraph wires. The effects on the telegraph system were catastrophic and bizarre. In Boston, telegraph operator Cornelius Van Horn was working the night shift when his telegraph key began operating by itself, sending messages without human intervention. The electromagnetic interference was so strong that the telegraph wires had become charged with enough electricity to function without their usual power source. In many locations, telegraph operators received severe electrical shocks. Some were knocked unconscious. Telegraph wires sparked and caught fire, igniting telegraph poles and spreading flames to nearby buildings. The main telegraph line between Boston and Portland burst into flames in multiple locations. In Europe, telegraph systems from London to Berlin failed simultaneously. Perhaps most remarkably, some telegraph operators discovered they could disconnect their power sources entirely and continue sending messages using only the electricity being generated by the electromagnetic storm. On the line between Boston and Portland, two operators held a 2-hour conversation using nothing but the power provided by the aurora. The failure of the telegraph system had profound consequences. Financial markets, which had become dependent on instantaneous communication, were thrown into chaos. News of important events couldn't be transmitted. Government communications broke down. For the first time in the modern era, humanity got a taste of what would happen if our technological infrastructure suddenly vanished. But the 1859 event was about more than just failed telegraphs and pretty lights. Scientists and amateur observers around the world began to piece together what had actually happened. Carrington himself made the connection between the solar flare he had observed and the subsequent electromagnetic disturbances on Earth. This was revolutionary thinking, the idea that events on the Sun, 93 million miles away, could directly affect technology on Earth was almost incomprehensible to the Victorian mind. The great German mathematician Carl Friedrich Gauss had been studying terrestrial magnetism for decades, and his protege Alexander von Humboldt had coined the term magnetic storm to describe sudden disturbances in compass readings. But the Carrington event provided the first clear evidence that these magnetic storms originated from the Sun itself. In the United States, the Smithsonian Institution began collecting reports of the aurora and its effects. They received over 1,500 accounts from observers across North America, creating the most comprehensive record of a geomagnetic event ever assembled. These reports revealed the truly global nature of the phenomenon. Aurora had been visible as far south as the Caribbean islands, Hawaii, and even near the equator. The scientific implications were staggering. If the Sun could affect the Earth so dramatically, what did this mean for our understanding of the universe? The event helped establish the new science of space weather and laid the groundwork for our modern understanding of the solar-terrestrial connection. But perhaps most prescient was the realization by a few forward-thinking scientists that this event was not unique. Historical records, when carefully examined, revealed evidence of similar events in the past. Ancient Chinese astronomers had recorded unusual aurora displays. Medieval European chroniclers had described nights when the sky burned red as blood. The Carrington event also revealed something troubling about the nature of such storms. Analysis of the historical record suggested that extreme geomagnetic events like this occurred roughly every 50 to 100 years. This meant that another Carrington-level event was not just possible, it was inevitable. As the immediate effects of the 1859 storm subsided, life gradually returned to normal. Telegraph systems were repaired, often with improved insulation and surge protection. The initial shock gave way to curiosity, then to a kind of collective forgetting. The Carrington event became a historical footnote, a curious Victorian scientific anomaly. But some scientists continued to worry. As technology advanced and society became increasingly dependent on electrical systems, they realized that a repeat of the Carrington event would be far more devastating to the modern world than it had been to the Victorian era. In the decades that followed, our understanding of solar storms grew more sophisticated. We learned that the Sun goes through regular cycles of activity, with periods of high and low solar flare activity roughly every 11 years. We discovered that solar flares and coronal mass ejections are caused by the sudden release of magnetic energy stored in the Sun's corona. We began to monitor space weather with the same attention we pay to terrestrial weather. The development of the electrical grid, radio communications, satellites, and computer networks has created a world far more vulnerable to electromagnetic interference than the Victorian telegraph system ever was. Modern studies suggest that a Carrington-level event today could cause trillions of dollars in damage,
knock out power grids across entire continents, disable satellite communications, and potentially set back technological civilization by decades. In 2012, Earth narrowly missed a Carrington-scale solar storm by just 9 days. The coronal mass ejection passed through Earth's orbital path, but our planet was safely out of the way. Scientists estimated that if this storm had hit Earth, it could have caused damage equivalent to 20 Hurricane Katrinas. Today, space weather monitoring has become a critical field of research. Satellites stationed at the L1 Lagrange point, about 1 million miles from Earth, provide early warning of incoming solar storms. Power companies have developed protocols for shutting down vulnerable systems when extreme space weather is forecast. Airlines reroute flights away from polar regions during solar storms to avoid radiation exposure and communication blackouts. Yet, despite all our preparations, we remain fundamentally vulnerable. The Carrington Event serves as a sobering reminder that we live at the mercy of our star, and that the sun that gives us life is also capable of destroying the technological civilization we've built. Richard Carrington died in 1875, 16 years after his momentous observation. He probably never fully grasped the significance of what he had witnessed that September morning. His careful documentation of the solar flare, combined with his hypothesis connecting it to the subsequent magnetic storm, established him as one of the founders of space weather science. The Carrington Event remains the benchmark against which all other solar storms are measured. It was a moment when the cosmos reached down and touched human civilization, revealing both our remarkable ingenuity in harnessing electromagnetic forces and our profound vulnerability to the very forces we thought we had tamed. As we continue to advance technologically, becoming ever more dependent on electronic systems, satellites, and global communications networks, the lessons of September 1st and 2nd, 1859 become increasingly relevant. The Carrington Event reminds us that we are not separate from the universe around us. We are part of it, subject to its whims and connected to the star that burns at its center. The next time you see the northern lights dancing across the sky, remember Richard Carrington and his morning observation. Remember that you're witnessing the same fundamental forces that once set telegraph wires on fire and allowed operators in Boston to send messages to Portland powered by nothing but starlight. And remember that somewhere 93 million miles away, our sun continues its ancient dance of creation and destruction, holding within its magnetic fields the power to transform our world in ways we're only beginning to understand.